Hi, in this video we show how elasticity of demand may be used to decide how the unit price should be adjusted in order to increase revenues. This video builds on an example seen in a previous video where we computed and interpreted the elasticity of demand for a publishing company selling textbooks. We will elaborate a bit more on this example to illustrate the theory introduced in this video. Recall that we have defined the elasticity of demand as minus f prime of p times p over f of p, where f of p gives what the demand is for a particular product as a function of its unit price, p. It is obtained by solving for the demand x, the demand equation. It compares instantaneous relative changes of the demand over the unit price. Therefore, when the unit price is p dollars per unit, an increase of 1% of the unit price gives a decrease of E of p percent of the demand. In the example presented in the previous video, we had E of 175 equals 0.39. Therefore, when the unit price is $175, an increase of 1% of the unit price gives a decrease of 0.39% of the demand. Note that in this particular example, the relative change of the demand, which decreases by 0.39%, is less than the relative change of the unit price, which increases by 1%. Because we are not losing too many clients by increasing the unit price, it is worth asking whether it is worth increasing the unit price slightly in order to increase the revenues. The idea here is that the revenues might go up if the demand does not decrease too much. How much is too much is what we need to figure out. Because if the demand decreases too much, even if we sell at a higher price, the revenues might still go down. So the big question is, at which value should we set the unit price in order to maximize the revenues? The revenue function R is the unit price P times the demand X. Since we can express X as a function of P, then R is a function of the unit price, and R of P is P times F of P. If this function F is differentiable, then R is the product of the differentiable function F of P with the linear function P, and therefore R is differentiable as well. To differentiate this product, we, of course, apply the product rule. Therefore, we differentiate with respect to the variable P, and R prime of P is equal to the derivative of P times F of P plus P times the derivative of F of P. This gives 1 times F of P plus P times F prime of P. To see where elasticity of demand comes into play, I will factor out F of P, and in the bracket is what we get by dividing both terms in the previous expression by F of P. Now, adding is the same as subtracting the opposite, and in red you will recognize the expression for the elasticity of demand. Therefore, I prime of P is the demand F of P times 1 minus the elasticity of demand. Because the demand is always a positive quantity, the sign of R prime of P depends on the sign of 1 minus the elasticity. Therefore, if E of P is less than 1, and economists will say that the demand is inelastic, then 1 minus E of P is positive, and R prime of P is therefore positive, so the revenue function is increasing. This means that increasing the unit price will increase the revenues, in the case where the demand is inelastic. Similarly, if E of P is larger than 1, economists will say then that the demand is elastic, then 1 minus E of P is negative, and R prime of P in that case is negative. So the revenue function is decreasing. This means that increasing the unit price will decrease the revenues. When E of P equals to 1, then the demand is said to be unitary. Increasing or decreasing the unit price by a small amount will have little effect on the revenues. This might be a unit price for which the revenues are maximized. The following graph summarizes the information. Pictured is the graph of the revenue function used as an example in the previous video on elasticity of demand, where we were interpreting values of the elasticity for a publishing company. As we can see, the revenue function can be maximized, and the optimal unit price is the first coordinate of the vertex of the function. To the left of the vertex, the revenue function increases and demand is inelastic. To the right of the vertex, the revenue function decreases and the demand is elastic. At the vertex, demand is unitary and the derivative is 0. We had computed that E of 175 is 0.39. Since elasticity of demand is less than 1, so inelastic, this indicates that at a unit price of $175 per unit, the revenue function is increasing. Therefore, the optimal unit price is larger than $175 per unit. Here is an example of a problem you may have in the exercises. Given the demand function P equals 10 to the minus 6 x squared plus 400 for selling X textbooks, where P is the unit price per textbook, use elasticity of demand to maximize the revenues. Note that this problem uses the same demand function as the running example used in the previous video. Since the revenue is maximized when its derivative is 0, or equivalently when the elasticity of demand is unitary, the optimal unit price is obtained by equating the elasticity of demand to 1. Below are the different steps necessary in order to obtain the elasticity of demand. This was already done in the previous video, so we list them without comments. Therefore, E of P is equal to P over 2 times 400 minus P. When the revenues are maximized, it is equal to 1. We want to solve this equation for P in order to recover the optimal unit price. We start by multiplying on both sides by 2 times 400 minus P, then multiply the right-hand side by 2, add 2P on both sides, and finally divide by 3 to get an optimal unit price of $266.67 per unit. Replacing this value into f of P gives the corresponding demand, which is of 11,547 textbooks. By multiplying the demand by the unit price, we get the maximum revenues, which is $3,086,438.58. On the following figure, we have added the corresponding coordinates of the vertex. Thanks for watching.